Imagine towering, jagged mountains of limestone, shrouded in mist, rising impossibly from a flat, green plain. Or picture incredible underground cathedrals dripping with mineral formations carved out over millennia. These aren't just breathtaking sights, they're dynamic landscapes, sculpted by powerful, often unseen forces. Today, you and I are taking a deep dive into karst landforms, specifically those found in the humid tropics.
Yeah, we're going to try and unravel the mystery of what these unique geological formations actually are, how they come into being, and perhaps most importantly, why they're so vital to both our planet and human societies. Our mission today is to pull out the most compelling insights from our sources, giving you that shortcut to truly understanding this incredible topic.
I'm really excited for this. Whenever I see photos of these landscapes, I'm just struck by how alien they look. So let's start with the absolute basics. What exactly are karst landforms? What makes them so distinct?
Well, at their core, karst landforms are a very specific set of geological features. The real secret to their existence lies in the rock they're primarily made of, carbonate rocks, like limestone. The key characteristic here is their exceptionally high solubility, meaning they literally dissolve, but they don't just form anywhere. They require very particular favorable conditions to emerge.
Dissolve, you say. That's fascinating. I always thought rock was, well, solid. What is it about limestone that makes it so prone to this kind of shaping?
That's where it gets really interesting. Limestone is predominantly made of calcium carbonate. Now, while calcium carbonate is insoluble in pure water, it's highly soluble in acid. And for these dramatic formations to really take hold, limestone needs to be at least 80% calcium carbonate. That's when it becomes incredibly susceptible to processes like carbonation and solution, essentially being eaten away by acidic water.
So it's not just the chemical makeup, but also its physical structure that plays a role, right? Like, are there tiny pathways for this acidic water to seep into?
Precisely. Limestone isn't a completely solid block. It has what we call natural lines of weaknesses, things like joints, which are cracks, and bedding planes, which are the horizontal layers where rock was deposited. These aren't just minor flaws. They're crucial because they act as conduits, allowing that acidic water to penetrate deep inside. This paves the way for weathering, the breakdown of rock and fluvial erosion, the movement of material by water, and even mass movement. All these processes work together, contributing to karst formation. And the rate of weathering, in particular, is most intense exactly where these weaknesses intersect, creating hotspots for dissolution.
That makes a lot of sense. So where in the world are these spectacular dissolving landscapes most common? We're focusing on the humid tropics today, but where are the global hotspots?
You'll find karst landforms globally, but the humid tropics truly are their grand stage. Think southern China, particularly Guangxi province, which is iconic, and then across Southeast Asian countries. Northern Vietnam, Thailand, Indonesia, and parts of Malaysia like Sabah and Sarawak. They also appear in southeastern India, Central and South America, and even Australia. For a broader perspective, they're also present in parts of Europe, such as the UK, France, and Slovenia, but typically less dramatically.
They give us a great geographical picture. Now, when we talk about karst, there are a few iconic shapes that immediately come to mind. Let's dive into the big three, the distinct features of these landforms. How do we even begin to differentiate them?
Well, we can differentiate them by whether they're on the surface or underground, and by their shape, height, and the angle of their slopes. But what's really important to grasp is that all of them are the product of prolonged weathering, fluvial erosion, and mass movement, patiently sculpted over eons.
Let's start with cockpit karsts. When I hear that name, I think of a landscape dotted with, well, pits. What do they actually look like?
If you're trying to picture it, imagine an egg box topography. Cockpit karsts are essentially a landscape of star-shaped depressions, which are the cockpits themselves, separated by roughly equally spaced conical or cone-shaped hills. The local relief, or the difference between the high and low points, can be quite significant, ranging from about 30 to 300 meters. The cones themselves are pretty symmetrical, with slopes typically between 45 degrees and 60 degrees, and they usually stand between 30 to 120 meters tall. You'll often see a high density of them, something like 15 to 30 hills per square kilometer, which gives it that distinctive, almost uniform pitted look.
And for anyone who's seen them, the iconic chocolate hills in Bohol, Philippines are a perfect example. They're just mind-boggling. But then you have tower karsts, which look like a completely different beast. How do those compare?
Yes, tower karsts are indeed a different beast. They're a steeper, much higher variety of karst risers, and what's fascinating is that they often develop from the further deepening of those cockpit karsts we just discussed. They characteristically rise very sharply, almost vertically, from the surrounding plains.
So they're not just bigger versions, it's almost like a next evolutionary stage in this geological process.
That's a great way to think about it. They show much greater variability in size compared to the more uniform cone karsts. They can reach over 150 meters in places like Sarawak, and an astonishing 300 meters in Vietnam and southern China that's almost 1,000 feet tall. But despite their height, their density is much lower, typically only 5 to 10 hills per square kilometer. They have very steep, sheer sides, often 60 degrees to 90 degrees, with striking cliffs, overhangs, and solution notches at their base where water has eroded them. They usually appear in groups, separated by flat alluvial plains, swamps, or rivers. And here's a curious detail. Their height-diameter ratio is often less than 0.5, meaning they're 2 to 3 times as tall as they are wide, which explains their slender, imposing appearance.
When you describe them that way, the images that immediately leap to mind are the famous Halong Bay in Vietnam, with its nearly 2,000 tower karsts that have evolved over an estimated 20 million years, and the striking tower karsts of Guangxi province in southern China. Just breathtaking.
Absolutely. And then we go underground to the third major feature, caves. These are crucial openings deep within the earth where water circulates. They are by far the most significant subsurface features in limestone terrain, far larger and more numerous in limestone than any other rock type, precisely because of limestone's solubility.
And when you're lucky enough to explore one of these caves, you see those amazing dripping formations that look like something from another world. What are those called?
Those are called speleothems, and they're truly unique formations within caves. You'll see things like stalactites, which hang from the cave ceilings like elegant icicles. They often start as very fragile, hollow tubes, barely thicker than a drinking straw, which is why we call them soda straws, before they gradually thicken over time. Then, growing upwards from the cave floor, you have stalagmites. These typically have a more rounded or cone shape and form from water drops falling from above. And when a stalactite and a stalagmite meet and fuse together, they create a majestic column.
So we've covered what these incredible landforms are and what they look like. Now let's get into the how. What are the powerful, patient geomorphic processes that actually sculpt these landscapes? It feels almost impossible for rock to be shaped this way.
It's a slow, powerful dance of nature. The overall process of karst formation involves the dissolution of soluble rocks, both on the surface and deep underground. The key players are chemical weathering processes, predominantly carbonation and solution, working in tandem with fluvial erosion and mass movements. They're all interconnected.
Let's try to picture this step by step. How do we get from a flat limestone surface to those pitted cockpit karsts?
Okay, think of it in stages. In stage 1, precipitation rain or snowmelt begins to infiltrate those existing weaknesses in the limestone, the joints, and bedding planes. At the points where these joints intersect, carbonation begins. This is where water, having absorbed carbon dioxide from the atmosphere and decaying vegetation, becomes a weak carbonic acid. This acid then starts dissolving the calcium carbonate in the limestone. Frequent rain in the humid tropics really accelerates this, deepening these initial depressions. Vegetation also plays a huge role here through both biophysical and biochemical weathering, basically helping to break down the rock and make it more soluble. Eventually, surface water flows find their way to the lowest points of these depressions.
Okay, so the water carves out little dips first.
Exactly. Then, in stage 2, you get what we call differential weathering. Imagine areas where the joints are denser water can penetrate more easily, so these areas weather faster, deepening those initial depressions. Areas with less dense joints weather slower, forming the conical hills. Over immense periods of time, this creates that distinct network of interconnected, star-shaped cockpits separated by the conical cones.
That's a powerful transformation from one form to another. So if cockpit karsts are a starting point, how do they evolve into those dramatic, towering forms we see in places like Halong Bay?
Well, the evolution from cockpit karsts to tower karsts is essentially a process of intensification and deepening over vast timescales. In stage 3, the continued chemical weathering, that carbonation and solution, along with fluvial erosion and bioweathering, continues to deepen the cockpits and make the cones taller.
And then what's the tipping point? What makes them shoot up into towers?
All right, so in stage 4, as the base of the cockpit gets lower and lower, eventually reaching the water table, the water can no longer simply drain downwards. Instead, it starts moving laterally, flowing horizontally. This lateral flow aggressively erodes the base of the conical hills, creating solution notches and undermining them, which can also lead to the formation of caves at their base. This weakening of the slope, combined with mass movement, causes the cockpit to widen dramatically, transforming it into a flat alluvial plain, leaving the cone standing as a steep-sided tower karst. And if these towers are in coastal areas like Halong Bay, wave action and salt weathering also play a significant role in eroding their bases.
Okay.
Finally, in stage 5, these tower karsts are fully formed, rising sharply from the surrounding plains, rivers, or swamps. And sometimes tectonic uplift can even reactivate vertical erosion, making these towers even taller.
It's astounding to think of landscapes changing so dramatically over millions of years. Now, about those incredible underground caves, how do they get carved out?
The formation of caves also follows a very specific sequence, essentially a hidden world being sculpted beneath our feet. Stage 1 begins with rainwater. As it falls and seeps into the ground, it absorbs carbon dioxide from the atmosphere and from decaying vegetation in the soil. This transforms it into that weak carbonic acid solution we talked about. This acidic water then seeps into ground cracks and pours into limestone.
Okay, same acidic water as before.
Yep. In stage 2, this acidic water slowly but relentlessly dissolves the calcium carbonate, carving out tunnels and cavities, often along those lines of weakness. As the rock dissolves, the weathered materials are transported away by underground streams, which also actively erode and enlarge the passages. Walls and ceilings can also collapse due to mass movement, widening the spaces even further. Initially, these networks of passages are completely submerged, filled with water.
So the initial carving happens entirely underwater.
Exactly. Then, in stage 3, a significant change occurs. This could be climate shifts, like a lowering of sea levels, or tectonic uplift that causes the land to rise. Either way, the water drains out of these submerged passages, leaving behind the dry chambers that we recognize as caves today. And finally, in stage 4, even after the cave is dry, ongoing rainwater continues to seep through the rock above. This water, still carrying dissolved limestone, drips from the roof, forming stalactites. And as those drops fall to the floor, they create stalagmites growing upwards, completing the cave's ornate decorations.